All right. I don't know whether this computer is getting more and more off, or whether this computer is getting more and more off. But as long as one of them says it's 9 o'clock, then I'll get started. They're off by almost 2 minutes now, which is interesting. Last time we were continuing to write our linked list. We started the actual linked list file. We wrote the fields, we wrote the constructor, and we wrote our first couple of methods. One of the more challenging ones, add at the end, and one of the very easy ones is end. We're going to start off today by writing a helper function that is going to be useful to us throughout the rest of the program. It's going to save us a lot of time and copying unnecessary code. And the reason we're not going to do the add in the middle immediately is that add in the middle is going to use this helper function. So have we written helper functions before in our code? What do we know about, say, the privacy of a helper function? Yeah.
Pretty sure that with any kind of, well, you know what, I'm gonna actually withhold my opinion on this because I don't quite know.
That's fair. So a helper function is not meant to be called by the end user. It is meant to be called by our code and only our code. Because of this, we can straight up make it private. It's not going to be visible from the outside. So we are going to start with private, and it is going to return a node. We're going to call this find node before. And it is going to take just an index. The reason this is useful is given an index, we want to be able to find the previous to that. And if you've done any kind of looping in the past where you're keeping track of a current and a previous until the current reaches something and then you do something with the previous, that's what this is going to do. It's going to identify the previous in a single loop. And that way we only have to write that loop in one place rather than all over the place in our program. If you're thinking in general or planning about the future of a linked list, you might think whenever I'm doing something in the middle of that list, I'm going to need to make a connection between the previous node and the node that I'm inserting, or the node after the node that I'm removing. Or so keeping track of a previous is always useful. So being able to have that isolated to a single piece of your code, a single part of your code, you're factoring it out of all of the future places that you would have it. On the other hand, maybe you don't think of this ahead of time. And as you're writing all of these functions, you think, I am finding the previous node a bunch of times. Or how have I done this before? In the add, I wrote this loop that found the previous. Now in the middle of remove, I'm doing exactly the same thing. You can go back and modify the code that you've written to factor that out into its own method. Rather than go through that tedious process, I'm just going to say, we will be using this in multiple places. So let's just go ahead and write it. Rather than taking in a node, it's going to take in an index. And this is because every time we call this, it's going to be based on the index. We're always going to know the index of the node we want to find the node before, the previous node to that of. So how would we do this? Given that we have a particular index, what do we want to do? Yeah. Some kind of loop. That seems useful. So I'm going to at least write the word while, because I don't think we really want to do this as a for quite yet. We probably could. Is there anything that we need to start with before we hop into that loop? Yeah. We might want to throw some kind of index out of bounds exception if the index is out of bounds compared to the size. If this is our code, we would hope that that's never going to be the case. Since this is private, the only thing that's going to be calling this is going to be our code. This is not the user giving us this index. This is giving us this index. So if that kind of exception being thrown is useful to your own debugging, we absolutely can. Then we can check if. What is our condition here? What's going to identify when index is out of bounds? Less than 0 or greater than size. What happens if it's exactly equal to size?
It would also be out of bounds.
Yes, so we want this to be greater than or equal to size because we're starting at something that's 0 indexed. So the last legal in bounds position is going to be size -1. What happens if we want to identify the tail? Would we want to be able to find the node before something out of bounds and have that be the tail? Is there ever a use case for that? Curious, isn't it? Thinking of the use cases of find node before, that's going to be for add in the middle or remove in the middle. But it is possible that the user specifies, I want to add in the middle at the end. In that particular case, what would we be passing this find node before? I'm going to leave this as greater than or equal to for the moment. And when we actually go write the code, for the add and remove, we'll come back to this and ask that question again. And I think that will help us to come back to this point and figure out whether this should go back to being strictly greater than size. But if we leave it as greater than or equal to size, at least our code won't crash on that case. It'll at least, worst case, give us an exception where we're not expecting an exception. All right, what other setup? We haven't written size yet. There should be a call to the size method.
Index.
Sorry?
Index before you're greater than or equal to.
Yep. Anything else we need to consider before we start in on this loop? What setup do we need to do? Yeah.
I had 2 nodes, one that was equal to this side and one still this side.
Okay, we could absolutely do that. I'm gonna argue we only need 1 node. That's a good idea and that would work. You'd have to have a check though to make sure that the size was greater than 1 before you set to this dot head dot next. I'm gonna set something just equal to the head for the moment. So we're gonna make a singly linked node of E. We're going to call this cur and set this equal to the head. Note again, we're not making a new node, we are just making a new name for an existing node. So whatever the head happens to be, we're going to make another name for that called cur. And cur will change and eventually no longer be the head, but again, we're not creating a new node, thus no new, no call to the constructor. This is just an assignment of an existing name to have a second name, if you will. Anything else we need to do to set this up? How are we going to know when we're done? Yeah.
I had I equals 0.
Yeah, we want some kind of counting variable. This is going to tell us the index. Since we're passing in an index, we need to know when we reach the index. We're not going to be comparing to node values. We're going to be comparing to the position in the list. So we need to know as we start to approach the associated index. So now we should be ready to write the condition for the while loop. What is that condition? While I is less than index. Pregame, what makes you say this?
Because we want the one right before that index.
Yeah, so while I is less than index, we want to continue doing something. When is this going to stop? What is the value of I going to be when we stop? Index minus one? Let's say the index we are trying to reach is 10. Find node before says we want to return the node at index 9. So index is 0. Is 0 less than 10? Yes. Is 1 less than 10? Is 9 less than 10? Yes. So the first time it's going to be false is when I is 10. So I think we actually want this to be index minus 1. Because that's going to stop. The first time it's false is when I is going to be the value of the node before the index that was passed in. Does that make sense to everyone? Very easy off by one error to make, yeah.
What if you had like the index was 9, but I is 2 or whatever, then it would still be true.
Right. Yeah, the idea is we're gonna be marching down the list until we get to the node before the index that's passed in, and we want to return that node. I can draw that out if that helps it make a bit more sense. Let's do that. I'll use a smaller example. So let's say we have a list and the index that we want to return the node before is 2. So it doesn't matter what's here, this point's here, doesn't matter what's here, this point's here, doesn't matter what's here, this point's, doesn't matter. Doesn't matter if it's the end of the list or if this list continues onwards, but the idea is the index that's passed in is this. If we pass in this index, we want to return this node. Not this index, but this actual node structure itself. And that's going to help us identify the previous if we wanted to do something like add in between here and here. So do something with this connection to add a new node in the middle of this. Or remove a node at this position or this position. If we need to remove this node, then we need to modify this pointer to point past this if we're going to remove it. So we always need that node before the particular index that we want to add at or remove at. All right, so thinking about what's this value of index is 2, I starts out at 0. We're going to loop bumping up I until we want I to be the index of the node that we want to return, which is 1. So the question we would ask is I less than index minus 1? Yes, 0 is less than 1, so we would continue and bump up I. Now I is going to be pointed here. Is I less than index minus 1? Is 1 less than 1? No, when we terminate the loop, I has the value of the index of the node that we want to return. If we said less than index, that would still be true, and we would bump I up to here, passing over the node that we want to return. Questions on that? Okay, so as we do this, all we need to do inside of this loop is what? Yeah. Yeah, we want to modify the node that current points to. What else? Yeah, we need to bump up our counter. So since we wanted to return the node, cur is pointing at the node and I is pointing at the, or is keeping track of the index. When I reaches that particular point where we terminate, now cur is the node that we are ready to return. So once we are done with this loop, all we have to do is return the node. And that matches the return type that we said we were going to return, a node of a generic type. Questions on this helper method? Yeah. Yeah, since we're actually just doing the I++ down here, we totally could. I'll just write that here real quick. Any preference as to whether we use the while loop or the for loop?
Or it makes more sense when you have an index.
For makes more sense here. We agree, we can get rid of this. Do this the for. Disagreement. It wouldn't be a programming class if we didn't have options and people didn't like those options differently. Honestly, what I can do here is I can comment one of them out rather than delete it.
I don't understand the structure of the flow, like what goes in there.
Yeah, so let's actually just quickly talk about that. So this int I equals 0, that is a setup, that is the declaration of a variable that only needs to exist within the scope of this loop. Because in a for loop, once this loop ends, anything declared in here is out of scope. Whereas if you use a while loop, this is within scope for the entire method. So there is an important difference between the while loop and the for loop. It's just irrelevant within the scope of this program. We don't need to access this I, and you see that we don't anywhere after this while loop, assuming the for loop doesn't exist. So this local variable that's only used within the scope of the loop is going to go here. The condition, the loop termination condition, which you see as the while loop's termination condition, goes in the middle. This is the loop termination condition. And then this is what happens each pass through the loop. Note that we actually could make a completely blank for loop. Does anyone know the structure or the syntax to get rid of the cur equals cur.next?
Do you mean set index equal to 1 in the for loop? Should it be -1?
Yes, this is not equals 1, this is -1. Thank you.
Okay, that makes more sense now. I was like, why is it?
It's because I hit the wrong button and I didn't notice it. So just like we use semicolons to separate here, if you have multiple declarations that you want to make or multiple conditions, you can comma separate them. So you could add cur equals cur.next right there, since we're doing that as well. And now we have nothing.
So it basically just condenses it.
Yep.
Okay.
And this is still just an issue because of the I that we declared up here. Not a concern. As soon as we comment one of them out, then that problem goes away. Yeah.
I want to turn that like for loops are like a generic programming thing and more like advanced programmers do on whiles more often. Is that any reason for that? Or is that just personal?
Personal opinion. Question.
When you make your for loop like that, you still need the brackets, like just to have them in there.
You can get rid of the brackets as well. So if things don't have brackets, that means there's a single line inside it. That's dangerous in this case because what comes next is this return cur. If you get rid of the brackets, in this case, the first time you enter the loop, you're going to return a cur. you'll get the bug of returning the head. Rather than returning what you want. Now, sometimes this is what you want if you write an if with a single line, or a for loop or a while loop with a single line. That said, it creates very easy bugs. So my default is to always include the curly braces, especially if you go back and modify an aspect of your code, like, oh no, I need a second line to this loop. If you didn't put the curly braces in there, now you need to add the curly braces, or the only thing that's going to be looped is the first of those two statements. And then the second statement is going to happen a single time after that loop terminates. May create an infinite loop. If that second statement helps the loop terminate. So sometimes the curly braces are optional. In this case, we need them to say nothing else happens in this loop. Any preference for how I keep this syntax? Again, lots of options. I just kind of like to go over all of them and let you choose. I'm going to keep this for loop the way it is because I feel like it's not necessarily something you've seen before. And I will leave this commented out here so that in case you wanted some other way to do it, you can see that comment also works for this logic. In general, you don't want to submit production code with comments like this in it. But in a class, when it can help with learning, absolutely. All right, we have our find node before. Great. Now we can go back and write our add in the middle, because that will use our find node before. So just like what I added up here, the at override, you add that whenever you're implementing something from an interface or from a superclass of some kind. And note that it also doesn't do anything for the compilation. It doesn't need to be there. The compiler doesn't need it. That said, the clarity from a programmatic standpoint says, I am implementing something that was defined either in an interface or a superclass above this. Yeah, it says that we are using, when this implements list of T, that is where we are getting this add from. We're defining something or giving implementation for something defined in that interface. So since add in the middle is also defined in that interface, we are again going to add at override to this. And now we are going to actually go back and implement that add in the middle. So this was public, again, returns a Boolean, whether we were successful or not. We're going to add in the middle. If we were to refer back to our interface, we would see that something in the middle needs both the index that we want to add at, as well as the element we are going to add. And that is a generic element. And as always, when you write these, that is going to be a red squiggly until you return that Boolean. That's okay. What do we want to do? This threw a couple of exceptions. So we're going to throw a null pointer. And what else were we going to throw? A legal argument. Great. So now we can start to check for them. If we were going to throw a null pointer exception, what would cause that null pointer exception?
That element is null.
Yeah. It's all done. If we're going to throw a, all right, it should be the null pointer exception, not the illegal argument exception. How are we getting the illegal argument exception? Yeah, so index could be less than 0. What else
So it's just greater than the size.
Yeah. I think we want to do greater than or equal to size again, I think we do. I did size here as well. So I forget, yeah, we implemented is empty, I think we can just write the getter for size as well. Size is automatically implemented. I didn't make it size, did I? I don't think I did. It's good to me. Let's go back into our add. We will throw. We want to be illegal argument exception. Okay, the actual logic of adding in the middle. How are we gonna do it? First of all, are there any special cases to this? What would cause us to need to think about this differently? Yeah,
If someone gives it next to 0.
an index of 0? Sure, I like thinking about that. So before going into that, I think there is one thing we want to do no matter what. What is that?
See if the list is empty.
See if the list is empty, I think we'll be okay. We need to make the note though, I think regardless of where we are, regardless of the state of this list. We can make the node that we want to add. So let's go ahead and make a singly linked node of type T. We're gonna call this new node. Since we don't know exactly what it's gonna be yet, and or where it's going to be, we will, since this node doesn't exist, we need to construct it, which means we need to call the constructor. It doesn't exist in the list. It is being constructed for the list, so we call that constructor. And again, I guess we could use it like this and. All right, we want to pass in the element becomes the value in that node. Now we're ready to identify our cases. So the first case that was identified is if we are adding at the beginning of the list. If we're adding at the beginning of the list, does it matter what the current size of the list is? I don't think it does. Let's see if we can make it work without worrying about the existing size of the list. So we can identify this by saying if the index that was passed in is 0. If that index is 0, we want to add it at the beginning of the list, regardless of the current size of the list. So if index is 0, then what needs to happen? Yeah. Eventually, I think we first need to do something about new nodes next. Where should new nodes next point? Yeah. Start writing new node dot next. Sorry. Yeah, we want to make it the new head, but its next should point to. The existing head. If we've just made a brand new list, the existing head is null. So if it is the only node in the list, then it will point to null. If there is an existing node there, the head tells us exactly what is going to be the new second node in the list. So I think we can safely do that. There's one last thing we need to change.
Has to be forwarding node.
Yeah, we need to modify the first element of the list to be the new node that was added. That's it. That handles that case. Question?
Do we need to also increment the size?
We probably should do that. I think that I'm going to factor that out. Because for every one of these cases, we're going to end up needing to bump up the size. So actually, I'm gonna do that before I forget it. At the very end of this, I'm gonna say size plus plus before we return true. That'll be the end of the method. But there are gonna be multiple ways for which this can be successful. And so rather than type size plus plus for each one of those cases, we're just gonna do it at the end. Great point, though. Other questions? All right, we might have another case. Does it matter whether we're adding in the middle of the list or adding at the end of the list? Are they the same case?
If you're adding at the end, you'd have to change the tail.
Sure. So we could consider that as an if within this else. So I'm going to write this as just an else. Not after this. I did not copy everything. Yes, it did. So within this else, we're going to just assume that we are doing something, but yes, we do need to consider whether we are adding at the tail, but we don't want to separate those into completely different situations because only one part of this is going to be different between whether we're adding in the middle or adding at the end. So we're going to do all of the logic to add in the middle and then say, if we're adding at the end, change the tail in the middle of this else. I think that makes the most logical sense. So let's go ahead and how are we going to do this? Maybe I should draw something out here. Yeah,
We do not want to do an else if statement instead of each.
if we do an else if, there are going to be two more cases. I would argue we're going to bin everything together and within that else, after we've done everything to set it up, figure out, did we just add at the very end? If so, change the tail. That avoids copying unnecessary code. Now we need the node before the index though, don't we? Because we're going to be adding in the middle somewhere, which is going to use the code that we just wrote, this find node before. So we would need to do that here in the code, but since we already wrote that, we're going to utilize it. We need to identify what that node is going to be. So we are going to make a singly linked node. We're going to call it prev. Right. And we'll set this to be the result of the function call to find node before. This is just going to do all of the work that we specify in find node before that is going to give us the node before the query. Since the index is the position we want to add at, all the way back up here, we want to add at that index. The node before that index is going to be the work we just did. Now we have a name for it. We're going to call it prev. Questions on that call? What do we do with prev? How do we start adding right after prev and before prev.next? Yeah, we can start there. We can say new node.next equals prev. Let's actually draw out exactly what we're doing here, so we can make sure that we see it as well. Let's use that exact same case of 3 nodes. We're gonna call this prev. We're gonna call this the index we want to add out. The new node that we create should be at this same index in the list. So we are making a new node that we want to put right there. When we do that, 0, 1, 2, this becomes the new 0, 1, 2. It's the new at that index. Great, so we identified prev, that's this node. We want to change prev's dot next, that is pointing here, to instead point to the new node. As we do this, have we made an issue? Yeah, so we are not done with this yet, so we want to do something about the new node. This is our new node. Let me just name it so we know. We said new node dot next equals prev. Is that what we want?
Next should be prev dot next.
Yeah, I like that. New node dot next, this pointer is going to be prev dot next. So we want to make this connection right there so that this will, once we redirect this to point at the new node, make a new list. So we are going to say prev dot next. Great. What's the next thing we want to do when manipulating this image? Yeah.
Say prev dot next gets me then.
Yeah, instead of prev dot next pointing to this node, we want prev dot next, this arrow, to point to new node. So we want to make that connection. Really interesting sequence of instructions. New node dot next equals prev dot next equals new node. Without an image, that is confusing. So I really like the concept of drawing it out. As you draw it out, you can start to manipulate the arrows and realize what needs to happen in what order to accomplish what it is that you want to get done. As you're taking the 8th, this is one of the most important pieces of advice that I can give you. You will have 5 hours to do what is probably an hour worth of work, which means you can be very thorough. You are allowed paper. I would not, even if you think you know what you are doing, fail to fill up that paper with drawings, just making absolutely sure you're walking through the program and making sure that at every line you are doing something that makes sense visually as well as logic. So we've done this, great. What if we manipulated the tail? What if we just added something at the tail? Remember that index could be something like size. We could be wanting to add at the end. This node actually may not exist. If this node did not exist and we passed this as an index, when we say something like new node dot next equals prev dot next could be null. In which case new node dot next would also now point to null. The issue is if this were the tail, we don't want it to be the tail anymore. So we would need to manipulate the tail? Yeah.
So then would it just be a simple like if size equal to index
Yeah, if
new
index
tail? Or,
is equal to the size.
or this tail. This dot tail. Tail.
Something like that.
You have to put this dot tail or what is?
Since there's nothing locally that has the name tail, you can use tail. You could say this dot tail, that wouldn't break anything. I like to use this where there is any ambiguity. Although if you are referring to a field, then, but really, that's just up to you. Yeah,
We're throwing an exception when index equals size.
yes, we are. So I wanted to come back to this and ask the question, should this be greater than or equal to size, or should it be greater than size? It should just be greater than size. That's a great point. I also wanted to go back to, once we figured all of this out and went through the logic, I wanted to come back to find node before. If we're calling find node before with the index that could be the tail, do we want to throw an index out of bounds exception for greater than or equal to size? Now we do not. We just want to say greater than size here for that exact same reason. Other questions? I just saved this for the first time and it needs me to save that in order for this to be okay. Great. Questions about anything we've done so far? That is the entire ad in the middle. Almost fits on the whole screen. Question? Because if we're adding at the very end, the node before the node that we're adding is going to be the end of the list. That is a great point, and this would be a very easy bug to introduce. Because intellectually, you don't want to be thinking about, all right, the node past the end, but that's the node we want to add, rather than a node that already exists. That is a great point and a great question, yeah.
Why do we need the getter for size?
It's pretty useless at this stage. In general, anything in a collection has a size. So because of this, to be consistent with other Java type objects that are collections, we implement size because some external user will expect that that size exists and expect that they can call it. There's really no other reason from our own code's perspective. Yeah.
So far, what we've used, we could have just said size, not.
Yeah. Yep, size or this dot size, referring to that. Yep. Whenever you have a method with a line that's just return something that's a one line, you can always just substitute that directly back into your code. Yeah, the only reason we do it is because people expect it in collections. All right, let's spend the last 5 minutes of class thinking about get. If you finish get, you can start thinking about remove, but remember that get is just going to return something at a particular index. So if you'd like to talk to a person next to you, start thinking about what is the logic, given everything that we've constructed so far, how would we implement a get? If you get through that, then you can start thinking about remove before you remove yourself from the classroom.
Who's the first thing you have to try? Use.
This is odd.
We just have to do like find out before and then just return find out before's dot next.
Interesting way to think about it.
That is an interesting way to think about it.
That's fine. Yeah, because we've written find node before, that is incredibly easy.
Yeah, we already read find out before, so we just need to return find out before dot next.
Yes.
Oh, even easier.
Oh, that's easy.
Yeah.
I like it like this. Yeah. Sorry. Mind of, we're not there.
Get the next one.
I will say that get is probably slightly more complicated than that in some edge cases. Are there some edge cases that you might need to think about?
Probably need to know if it's the first or the last.
That might create some challenges.
Yeah, so there's a little bit more.
It's the very first node, find node before that is gonna be out of bounds.
Yeah, so then you want the edge size equal to the zero or. size equal to zero.
Yeah, but the default case is very easy. I'll leave people to think about that between today and tomorrow. We'd like to give it a stab to implement get and or either one of those removes or both of those removes. That is my challenge to you, and we will implement them in class tomorrow. I have office hours starting for the next 2 hours, and I give 2 pieces of advertisement for those office hours. I have a little name tag with a status on it. I took an improv class last quarter. If you change what that says, I will do my best to act like that until someone else comes and changes it. Second, I have a dad jokes calendar. I am starting to pin up my favorites and leave the other ones throughout, so feel free to come by the office and peruse terrible dad jokes.